Okay, we've looked at molecules, we've looked at them forming. Now we need to look at the gas situation, right? We've seen them in crystal lattices, we've seen ionic bonds, covalent, polar bonds, etc. We now have to look at a different state. We have to have a look at the gases and what happens when we've got a gaseous situation, because let's face it, around us we're living in a gas the whole time. Air is a gas made up of various different constituents. If you go and look it up, you'll see there's nitrogens, water vapors, carbon dioxide, carbon monoxide, various other gases in trace forms, some that have got out of hand with regard to our pollution-ish situation, where we've got gases that are now basically, it's so bad in some places that it hides the sun. It's so bad in some places that it's affecting our upper atmosphere. We all know about this, the whole ozone problem, the greenhouse gases and things like that. But let's go back and look at the gases. Essentially, we start off with a model of a gas as being an ideal gas, right? Now, the ideal gas, it allows us, it gives us a way of just conceptualizing and imagining a gas. And then we start making subtle changes to the ideal gas situation much later on, right? Because we start looking at very high pressures, very high temperatures, very low temperatures, very low pressures and things like that. And it does deviate, right? Deviates for obvious reasons, but we don't have to discuss that at this point in time. Now, what is an ideal gas? Now, you know that every atom, every molecule is in a constant state of motion, even if it is sitting in a block of ice, right? Those little water molecules in their little lattice, their crystal, they are sitting there and they are vibrating. In a metal, they are vibrating. They have an energy built into them, right? Now, as we release them, as we, for example, produce a gas, okay? Now you know that hydrogen, under normal situations, nitrogen, oxygen, fluorine, they exist as gases, okay? So they are around us in the air. They are moving continuously in random patterns. There isn't a way of saying, that atom is going to, or molecule is going to go this way or that way. It's random. And don't forget, they're continuously bouncing off themselves, bouncing off various other things. So they are moving around continuous random motion. And that, as you remember, is called Brownian motion. That process of randomness we call Brownian. Brownian motion, okay? Well, we need to say to ourselves, right, what other things do gases do? Well, if you've ever had the misfortune of being in a closed room and somebody's opened a bottle of ammonia, what happens? If they open it on the far side of the room, it's not long before you smell that, right? What happened? How did it get to me? Well, the ammonia comes out of the container, and then each individual molecule, the NH3, gets bounced around until it starts filling the area it's around. So gases will fill the shape that they're put into, right? So if, for example, you put them into a cylinder, they will expand and fill the cylinder, right? Because their motion is random and they've got the energy to do so. So they fill up the space that they're in. In other words, over here, in the room I'm sitting in, it is full of air molecules, or air atoms, constituents of atoms, etc. And they are whizzing around, hitting the walls, hitting the ceiling, hitting me. Now, just think of this situation. What have we got? We've got a box, let's say. Let's take a box, shall we? There, right? And into our box, we put one molecule of air, or one molecule of oxygen, or nitrogen, let's say. Right? This poor guy is going to be pretty alone inside there. He's going to be bouncing around inside there, but there's only one of him. So he can't exert a force on this side as he hits this and hits that side. He can't exert enough to actually sustain a pressure, right? Because where does the pressure come from? The pressure comes from all these individual molecules of gas hitting the sides of the container that they're in, right? That's where the pressure comes from. So we have to start off by saying, right, let's look at pressure itself. Well, first of all, how do we measure pressure, right? Pressure is measured in something called pascals, right? So pressure is actually defined as a force per unit area, which is newtons per square meter, okay? That's a pressure. But that actually means then that those molecules, because they're hitting continuously, they're exerting a pressure, right? That thump, every time they hit the sides of the container, that's where the pressure comes from. Okay, now, well, what we've got is we've now got a gas, all right? Now we want to start changing things about this gas. We're going to start changing the pressure, we're going to change the volume, we're going to change the temperature, and we're going to change the amount of molecules of gas that we've got. Because obviously, if we just think logically, if we put one molecule in there, and if we put a gazillion molecules in there, it's going to be different, isn't it? Think of a balloon, right? If you give one puff, doesn't do much, does it? But keep putting more and more and more molecules in there, right? The balloon is going to expand because you're increasing the pressure the more molecules you put in, right? We're going to come to that as well. That's going to be Avogadro's law, okay? When we talk about these things, essentially there's going to be, let's say there's going to be 3 elements, 4 elements if you like. First of all, we're going to be looking at Boyles Law, right? And Boyles Law is where we're going to look at pressure basically, right? We're going to look what happens when we start changing pressure. Because if you've ever pumped up a bicycle tire, you'll have noticed that as you're forcing the air into there, right? What are you doing? You've got your little, you've got your bicycle pump. Let me just get my, not a bicycle pump, but we've got this tube, right? Over here like that, okay, in essence. Now, in the end here, right, we've got the valve that comes out to the wheel. This side we've got a plunger. So what are we doing? We are pushing air through the nozzle and into the bicycle tire, aren't we? So we are changing the volume here. We're making the volume smaller so the air goes out that way, right? That's what we're doing when we talk about the volume change. Temperature, okay, pretty obvious, isn't it? If you're going to heat up a kettle, for example, and do not do this, okay, because it is dangerous, but if you closed off the lid and boiled that water, that kettle would probably explode, right? And as I say, it's not something that we do, because as we're increasing the temperature, the pressure's going with it. We know these things intrinsically, right? We've seen it, we understand it, but we have to put it into a law, okay? Or a set of laws, all right? So let's first of all look at Boyles Law. Now, Boyles Law says that, let's just state it and you'll see it, the volume of a given mass of gas is inversely proportional to the pressure exerted on it, provided that the temperature remains constant. Okay, let us put down what he has said mathematically. He said here, the volume of a gas is inversely proportional to the pressure exerted. So let's put volume, let's put pressure. Inversely proportional means it looks like that, doesn't it? Okay, what does inversely proportional mean? Essentially, if we look at V and P, it means if V goes up, P goes down. Look, let's look. V is climbing, pressure is dropping. Okay, it's not the greatest parabola there. And similarly, it means that if V goes down, P must go up. That's inversely proportional, isn't it? Proportional is if one goes up, the other goes up. Inversely, they go in opposite directions, okay? As the lift goes down, the weight goes up. As the weight goes down, the lift goes up. That's basically inverse proportional. Well, you can see if the volume goes down, the pressure goes up. Well, let's just once again think of that in terms of a bicycle pump, okay? It's quite simple, isn't it? As I increase or as we decrease the volume, the pressure of that goes up. I am squashing it, right? What have we got? Let's just have a look at it and see, just so that we fully understand. What have we got? We've got a container here, right? And let's pretend that this is a circular container, and that's a piston that can go in. we've got a volume inside there, right? Remember? We've got our volume inside our pump. There it is. There's the volume, right? Now it's full of air, right? This is full of air. So what do we then do? Then what we do is we start pushing. We apply a force over here, right? We apply a force, which is over the area of the piston. So we are increasing the pressure, aren't we? As we increase the pressure on this thing, okay, the volume gets smaller. We're squishing everybody up, right? So we're forcing those molecules closer and closer together, okay? There's going to be a temperature issue coming in. You're all saying that already, because I'm sure you've felt the bottom of a bicycle pump after you've pushed it a few times. It gets pretty hot, doesn't it? So what's happening there? We are increasing pressure, decreasing volume, right? That's very straightforward. Similarly, if we went the other way, we pulled the piston out. We are decreasing the pressure, okay? And the volume gets bigger, doesn't it? So that's basically not only a relationship in a gas, it's a fundamental relationship of the shape itself, isn't it? Okay? So that's what Boyles Law is saying. It's saying that we have to be cognizant of the relationship between volume and pressure, right? Because a gas will occupy the space you put it into, right? Remember our ammonium molecule coming out. Please be careful. Very often the graphs are drawn like that. All right? Can you see what they've done here? V, and that's 1 over pressure, which means we get a straight line. Okay? Because if you take the graph above, which was a hyperbola, all right? Volume, pressure looked like that, remember? Be very careful of this here. It's usually a trick question, and they give it to you as a multiple choice question. I don't know, 2, 3 marks, whatever. And our intrinsic is to go with the parabola because that's what we learn it, but they've changed this to be a 1 over p. It becomes a straight line. Okay. The other thing, just out of interest, what have we got here? We said velocity. Volume is indirectly proportional to pressure, like so. Okay, so therefore we say V is equal to K over P, right? That's the proportionality constant K, and it's K over P. And if we look at that, that is analogous to a Y is equal to K over X, which is a hyperbolic shape, right? Hyperbola, let's put it that way. Right, that's the shape we're going to get. Okay, so that sorts out that one, right, which is in essence Boyles Law. The next one that we have to move on to is going to be where we change, for example, that was Boyles Law, all right. We just have to now say, okay, let's just look at the temperature, all right. What is temperature? Let's go back to last year or the year before. Remember, temperature is a measure of EK, the kinetic energy of the molecules, isn't it? It's a measure essentially of their speed, right? I'm using it as speed instead of velocity because I'm not going to bother about directions and things like it at this point. So what happens is T is proportional to EK, which is a half mv squared, and fundamentally we are not interested in, or rather the mass stays constant, so the temperature, okay, we say if we increase temperature, we increase velocity. T goes up, V goes up. T goes down, V goes down, right? Now let's ask ourselves, okay, how far down can we take T, right? We have to introduce the Kelvin scenario here, and a little bit of the understanding of what goes behind it. Well, we say, okay, we carry on and we freeze water. Great. We get ice. But the molecule is still moving, right? The question is then, how far do we have to go for the molecule to stop moving? How far do we go indeed? What are we doing? We are removing, we're slowing it down, but we are removing the energy, aren't we? We're taking energy away from that individual molecule. until it stops vibrating completely. At the time when it stops vibrating completely, we are at a place that we call absolute zero. All right? We have gone to absolute zero. What are we saying? Simple. We are saying that at absolute zero, there's no energy left in the molecule. It has stopped moving, and basically it's just fallen over and quit. Okay? That's what happens at absolute zero. Now, there's a nice little thingy. It was this. Temperature in Kelvin, right, is equal to temperature in degrees Celsius plus 273.15. That is being precise. Okay? Most of the questions, most of the textbooks give it as 273. Right? So therefore, at boiling point of water, Kelvin is going to be equal to 100 plus 273.15 is going to be 373.15 Kelvin. Freezing points, sorry, this is boiling point. Let's have a look at temperature degrees Kelvin for the freezing point. What have we got? 0 plus 273.15 is equal to 273.15. Okay. 273.15. All right. Okay. All right. Just put in my 0.15. That is freezing point of water. This is boiling point of water. Okay. Right. So what we've got here is we've got now another thing coming in is let us look at the temperature situation of these problems. Well, what happens if we change temperature? Now, there was a guy, a French chemist or physicist, Charles, and it became Charles's law. Charles's law, okay? And what did Charles's law state? Charles's law stated the following. It said the volume of a given mass of gas at a constant pressure is proportional to its temperature in degrees Kelvin or in Kelvin. Okay? The volume is directly proportional to its temperature. What does that mean? Well, if we draw it, we would say temperature, volume, directly proportional to each other like that. Okay? Now, interestingly enough, if we put, okay, or you can even change it around, okay, let's change it around and put temperature on the bottom scale and volume. If we put over here, okay, the temperature over here, 373.15 to 73.15, that is that, and this then, whoops, it's actually should be straight. Let me just, you know what, let me just make it straight. Okay, just so that it looks 100% right. Okay, okay, this goes through there, right, like that. Those are my points there. This is a certain volume, that's a certain volume over there. Okay, and essentially that's what we've got. All right, that is Charles's law, which is telling us that how could we see it? Okay, how could we see it? Well, let's, for example, if you took this you can do, if you took an empty plastic bottle, okay, and put a balloon over the top, okay, what happens is your balloon is just hanging there, right? Then take that bottle, it's a plastic bottle, and put it into hot water. Okay, boiling water. If you don't want to play with that, put it in hot water out of a tap. What happens? You will see that the balloon blows up. because what has happened is the temperature of the gas inside, the air inside, has been increased by the hot water, and it has expanded, right? It's moved further away from the other molecules, okay? The next session of this, we're going to go a little bit more into Charles' law. We're going to do Gay-Lussac's law.